Today we're going to have our second lecture on normalizing flow models. So let's do, again, a short recap. So remember, we've been looking at a few different approaches to the generative modeling problem. So we have a data set of high-dimensional objects such as images or text or audio or genetic sequences, some kind of high-dimensional data. And our goal is to learn a probability distribution, p theta, that approximates the true data distribution from which these images come from. And there's different ways that we have seen to represent the probability p theta. In particular, in the first few lectures, we've seen at least two ways. First, we saw autoregressive models. First, we saw autoregressive models which are based on the chain rule of probability. So they start by decomposing the probability of a high-dimensional object like text or an image x. They decompose that into a product over each component of x. So you can think of each xi as being a pixel. And they train a model to predict the next component, the next pixel, given the previous components. That has many advantages. One advantage is that it's tractable to evaluate the probability, which means that it's relatively straightforward to train this using maximum likelihood optimization using gradient descent. And that's actually quite rare that it's as straightforward to compute the log likelihood. So this makes these models useful for density estimation, for example. They also have reasonably high generation quality in many domains. But one problem is that they don't have a mechanism for learning features or for doing unsupervised representation learning. So to compensate for that, we looked at this other family called variational autoencoders, which are a latent variable model. They have these extra latent variables z here that can represent latent factors of variation in the data. But because we don't observe these factors, when we train the model, we have to perform this integral to compute the marginal density of x. So we have to train using an objective which can be potentially an intractable integral. And because of that, we have to perform a lot of machinery to approximate this intractable integral. And this is where variational inference comes in. So in the last talk, we saw one way of getting the best of both worlds. So getting a tractable latent variable model, so first of all, having latent variables, but also maintaining tractable log likelihoods. And this is where normalizing flows come in. By using normalizing flows, we can, at least in theory, get the best of both worlds. Now, again, there are some other difficulties that come in, but at least from this perspective, normalizing flows can get some of the advantages of both types of models. Although, as I mentioned in the previous lecture, the way in which these models are parameterized now has additional constraints. So that imposes a different set of problems. We have to be much more careful about the architecture of the neural net. And I'll talk about this again in this lecture. So let's recall what is a normalizing flow model. So in a normalizing flow model, we have latent variables z and observed variables x. And so we start with a simple prior over z, which can be something like a Gaussian, and then p of x given z is given to us by this mapping f. It's an invertible mapping, therefore it has a well-defined inverse, which we denote by f inverse. This is f inverse. And what's interesting is that this is a one-to-one mapping. So for each z, there is a unique x that is associated with this. So for each x, for each z, this probability density is just a delta function on a single point. But if we were to sample many z's like this, if we were to sample many of these z's, we can, so starting from a simple prior over p of z,
we could take many samples from Z, and then these samples get remapped in some way to the x's. And now the distribution over x can be more complicated because this function f has learned to remap by pushing certain things up, pushing certain things down. So it learns to remap the simple distribution, and now we can get something that's more that's a more complicated distribution for x. Right? So even though x here, each p of x given z is essentially a delta function, all the probability mass is just on one x. This still defines a valid distribution over it. This defines a valid marginal distribution over the x's. And what's more, this p of x is tractable for each x. For any x, we can compute this distribution. We can compute the density of x, or we can compute the log likelihood p of x, log p of x, via an approach called the change of variables formula, which you see here. So this is the main thing that we worked on deriving in the previous lecture. It's a formula for the density, or if you take the log, it will give you the log density or the log likelihood of x. You can get this. You can get now an exact formula for what p of x is. Now, because the mapping between z and x is 1-to-1, and p of x given z is a delta function, now you don't have to do any integral. There's a formula that precisely defines what p of x is. And this formula has two components. First, we start with x, and then we map it back to, you can think of it as z of x. So this is the unique z that is associated with that x. Then we look at its density under z, but that's not enough. We can't just go back and measure the density. There also has to be this adjustment factor, which is the determinant of the Jacobian. And if you remember, the intuition for why we needed that is because when we remap variables from when we change variables and we go from one density to another density, the overall support of that density can change both globally and also locally around each point. It might the global, if you think of z as being discretized, if you think of the space of z as being discretized into little squares, when we remap z to x, the volume of these squares might increase. So that one volume for that the volume of the distribution in one square could go to a larger square, but that volume has to roughly stay the same. Therefore, we have to adjust by the change of volume in each of these mini squares that are, the size of these squares would go to 0 in the limit, but we still have to make this adjustment. And the correct formula for this adjustment is this is the determinant of the Jacobian of the inverse mapping, which is what you see here. So in order to apply this formula, and that's something that somebody pointed out in the previous lecture, the determinant of this Jacobian has to be tractable. That's the main challenge. So we have this formula that works in theory, but in practice, we still have to compute this formula efficiently. And if you remember, a determinant is an operation that naively takes at least cubic time. So we have to do something with that. We have to choose an f that satisfies some number of conditions. First of all, this f has to be invertible, because otherwise we can't apply the change of variables formula. It also has to be expressive. So it has to be able to remap a really simple distribution like a Gaussian into something which is extremely complex, like the distribution of all the images of human faces. So it has to be very expressive. And finally, as I alluded to earlier, it has to be computationally tractable so that we can apply and optimize the change of variables formula in a reasonable amount of time. And again, naively, taking the determinant of an n by n matrix takes n cubed. So it's not any invertible function that will work here. And we saw a few strategies that could be used to construct these
these types of nice mappings F. The first strategy that we saw involved applying a sequence of simple invertible transformations. Or maybe I should not say sequence, maybe I should say composition. So we are composing many of these simple functions. So the dot here just means the composition of multiple functions. The circle means composition. So you can think of each simple transformation F as a layer of some sorts, but it's also an invertible mapping. So we can apply the change of variables formula to a composition. And we know that the determinant of the composition, so here the determinant of this composition equals the product of the determinants of each function. And so the hope there is that even though each function, each of these F's here is simple, when you compose many of them, it will give a mapping F that is still complex, but at the same time, its determinant will be tractable because it is the product of simple determinants. Each layer is still simple, and so the determinant of each layer is tractable, and the determinant of the full composition is the product of the determinants of each layer. Therefore, it will also be tractable. And again, as a reminder of an example of what a simple invertible transformation can be, we saw planar flows in the previous lecture, and we also visualized, and we saw that starting from a simple Gaussian, it looks, after composing 10 of these functions, we get something that looks highly multimodal and non-Gaussian. So that was the one example that we saw.
Should that ZM potentially be Fm minus 1? Or am I misunderstanding the formula?
Hold on. Yeah, I think there is a typo here. Yes, sorry, that's a good point. There is a, okay, this should be like this. Yeah, that is correct. So that was our first strategy. But I would say there's also potentially another strategy that could be followed. And here the idea is to directly work with the Jacobian matrix. So we can start by thinking about what would be a good Jacobian matrix, what kind of structure would make it tractable. For example, if it was diagonal, it would be clearly tractable. What other structures lead to tractable Jacobians? And can we starting from thinking about a Jacobian, can we go back and create interesting mappings? That's another general strategy. Now let me give you now an example of what I mean by that. One strategy that we're going to follow in this lecture is going to be to try to create mappings, invertible mappings, for which the Jacobian is triangular. What would be an example of that? So consider some kind of invertible mapping F that goes from X to Z. So F here in this equation is mapping Z to X, okay? And this is the general form of the Jacobian. So it's a matrix. Here, the rows are the rows are the different outputs of F. The columns are the inputs, and it's the matrix of all the partial derivatives. Imagine what happens if this function. So if the ith component, which is simply the ith component of the vector f of z, what if this component fi of z depends only on the components of z that come earlier in the ordering? So here we have a vector. The components have been ordered in some way for us, and let's imagine that each component each xi depends only on the zi that come before it in the ordering. In some sense, this is a little bit like an autoregressive model. Well, in that case, you can see that any entry of this matrix that lives in this triangle, right? So that would be dfj zi or something, where j would be here j would be less than I. Sorry, did I say this correctly? No, j would be greater than I. Okay, no, sorry, this is correct. Where j is less than I, this would be this would be 0, right? Because of this dependency structure. Anything that's in this block has to equal 0 because of this autoregressive type of assumption that I just made. And we know that if a Jacobian or if a matrix is triangular, then the determinant is simply the product of terms on the diagonal. Therefore, we can compute this determinant in linear time. So here I have another potential strategy for defining a tractable invertible mapping. Here, the determinant of any mapping that satisfies this property will be computable in linear time. And so this is going to be an insight that we're going to use in this lecture to define many other types of normalizing flows. And these are going to be much more advanced normalizing flows than the first example that we saw in the previous lecture. And this will also lead to some really interesting connections between normalizing flow models and autoregressive models. Okay, so that's going to be the plan for this lecture. Right? So we're going to be looking at a few types of flows with triangular Jacobians. There are some well-known models in this area. For example, some early models were NICE and Real NVP. If you're also familiar with the GLOW model, that's a little bit more recent. That is also based on a very similar structure as these Real NVP and NICE models. And then we're also going to talk about some connections between autoregressive flow, normalizing flow models in a middle part. And finally, I'll conclude by connecting these two ideas, connecting the ideas from flows and autoregressive models, and deriving an algorithm called parallel wavenet, which will allow us to define a wavenet type of model from which it will be fast to sample. And this is actually a practical algorithm that has been influential and that has enabled fast speech generation on many practical devices that you may be using. All right, so let's now look at an example of one of these new types of flow models in which we have a triangular Jacobian. So models that are based on this strategy that I started talking about. We're going to start with this model, which is called NICE, which stands for Nonlinear Independent Components Estimation. It is also based, so by the way, this idea of combining composing multiple transformations, it doesn't prevent, this idea is applicable in any type of flow model. So it's not like we're going to be discarding this idea of having a composition of flow layers that will always remain. And that's a central part of most flow architectures. And if you look at the implementations of these flows, they heavily rely on the fact that you can compose many layers like this. So we still have a composition of different flow layers in a normalizing flow model. What's interesting is going to be the choice of layers that we're going to use. So these Fs are going to be within two types of layers. So the NICE model defines what are called additive coupling layers and rescaling layers. And let me explain what these two layers are. So the idea of an additive coupling layer is to define, yes, the additive coupling layer is precisely the layer that defines this interesting triagonal Jacobian structure. And the way that it does that is by being a little bit clever
about how this transformation is performed. It starts by partitioning the input variables, right? So this layer has some input variables z. They're going to be transformed into an output variable x. And it starts by partitioning the z into two disjoint subsets, which are, it can be actually any subsets, but just for the sake of this explanation, I'm going to say that the first d components are going to be the first subset, and the remaining n minus d components are going to be the second subset. But you can choose an arbitrary subset. So we partition z into two subsets, and then we define the forward mapping z to x as follows. The first set of variables, the set of variables that are in the first subset, they get mapped into x without any transformation. Now, the second set of variables, they undergo this affine transformation, where they get, we add to them this additional term, m sub theta of z1 to d, and this m sub theta is a model that is just parameterized by a neural net. So this is some transformation of the first set of variables. So here, again, the output here is the output for the second set of variables. It receives the first. This is the output here is the output for the second set of variables. It receives the first. It receives the second subset of the input set of variables plus a transformation of the first subset of the input set of variables. This might be a little bit easier to understand via a picture. So I took a picture here that comes from the original paper. I apologize, in the paper they use a slightly different notation, but what we have here, so this, when they say x key, this actually means, so this is what we refer to as the first subset. This is z to 1 over d. And this one gets mapped without any changes to x from 1 to d. And then we also use it, we also take this first subset and we feed it into a neural net, M, which then gets combined with this other subset, zd plus 1 to n. So this is what this variable is. It goes into, so now the output x d plus 1 to n becomes the sum of this term plus the output of this neural net. These get added, and this is what gives us the output for the second subset. Are there any questions about this transformation? Okay. So that's how we define this. And again, this m sub theta can be just any neural network, and it has the input units because it takes as input the first d components of z, and then its output has n minus d components because it has to have the same shape as this vector. Okay, this is the forward mapping, and I claim first that this is an invertible mapping. Why is that the case? So let's, okay, this is the forward mapping. Here I'm just rewriting it compactly. We start by having an identity mapping over the first subset, and we have this more complicated formula over the second subset. So I claim that this is invertible. Why is this invertible? Well, let's define this. So first, if we were to go from x to z now in the inverse direction, so the inversion of the first set of components is easy. That's just the identity mapping. So z from 1 to d, that just equals x from 1 to d, because that's the identity mapping. What is more interesting is the other component,
And here we apply the following formula. So where does this formula come from? We can make a little drawing here. So here I have, remember the figure on the previous slide, it looked like this. Now I have x from 1 to d. That one is just getting remapped directly to get z from 1 to d. Now that I have z from 1 to d, I can compute m, right? Because I have this number, then I get to know the m that was added to this node, right? And now I have x, let me just call it x prime, that's the other part. So now to get z n minus 1 to d, I take this m, which is here, I subtract it from this x, which is what I'm doing here, and now I get this variable that I want. So here, because we have this interesting structure in our forward mapping, the inverse mapping is also completely invertible. So this now becomes an invertible mapping that we can use within a flow layer, within a normalizing flow layer. And it's called an additive coupling layer because we're coupling the two subsets of Z in an interesting way that also happens to be additive. Yep. So I guess I wouldn't really use the term constant to refer to M. M is most definitely a very expressive function, but it's a function of only this term, Z of 1 to D. And it is, crucially, it is not a function of this term, which is why things are invertible. This little trick wouldn't work if M, if we needed to have the second subset in order to compute M, then this wouldn't work. But because we have this part in the inverse mapping, which is exactly this part, this whole thing becomes invertible. Okay, so this is an additive coupling layer question. Okay, that's a good question. How big are these subsets? You can think of it as roughly being split into two halves. Okay. And in practice, if you look at models like real NVP and Glow, they're also very clever about how this partitioning could be performed, how this partitioning is performed. So you don't just take a random subset. If you have an image, you partition the image in interesting ways that. So in real NVP, they use this checkerboard strategy for partitioning the pixels to get better empirical performance. So there are also a lot of practical details about how you choose this partition, and it helps things. But for now, just, okay, I guess I'm explaining it at a slightly higher level, but there are some interesting implementation details about how you choose this partition. Okay, so that's an additive coupling layer. It's invertible. And now the remaining question is it tractable to compute the determinant of the Jacobian? So the answer is yes. What is the forward mapping? Well, again, the first part is the identity. The second part is the additive coupling layer. That's just what I had in my earlier slides. I'm just putting it here so we can see it. Now, what is the Jacobian of this forward mapping? Well, the Jacobian has exactly this triangular structure that we're looking for. So, and then it happens to have the identity on the diagonal. Therefore, its determinant is always going to be 1. So this is called a volume preserving transformation. Determinant is 1. So why does the Jacobian have this shape? Well, so this here is, this 0 here corresponds to, it corresponds to, sorry, this might be a little bit flipped. It corresponds to x from 1 to d. And this x from 1 to d does not depend on the input variables z n minus 1 to d. So there is, okay, sorry, I'm not great at drawing this arrow. So these two things are, there is no dependency between them. Okay, I apologize for my improvised drawing, but the point here is that this, so this component here with which this 0 is associated, no, sorry. This component here with which the 0 is associated does not depend on this component of z. Therefore, that's a 0. Does that make sense? Yeah. Okay. So this is a 0. Here we have this more complicated submatrix of the Jacobian, which will depend heavily on M, but it happens on the off-diagonal terms. So we don't have to compute it. And then you can see here that on the diagonal here, we have the identity because there is nothing that's, so we only have an additive modification to these z variables, right? X is everywhere a linear function of its corresponding terms. So this second subset of the output is a linear function of the second subset of the input. And the first subset of the output is the linear function of, in fact, it's the identity function of the first subset of the input. Because things are linear, well, it's not even linear, it's linear with a slope of 1. Therefore, the entries on the diagonal are just the identity. Let me know if that helped, if that makes sense or not. But the point here is that the Jacobian is triangular, the entries on the diagonal are 1, and therefore we have a volume preserving transformation, and the determinant is always 1. So we don't even have to include the determinant in our loss function. It's always 1 for any choice of M, right? So this is for any choice of this neural net M, which is really powerful. It means that we can use any architecture that we please within this normalizing flow layer, and it still gives us the kind of invertible volume preserving transformation that we're looking for. Okay, this was an additive coupling layer. Again, I want to reemphasize that the inverse can be computed for any M. And now I just want to complete the full nice model by mentioning the rescaling layer, which is much simpler. The rescaling layer, as the name implies, it's just a component-wise multiplication of the input by a rescaling factor S. This is the forward mapping. So S is going to be always strictly greater than 0. Therefore, the inverse mapping is also well-defined. It's very simple. It's just the division. And the Jacobian is going to be simply the diagonal of, well, the Jacobian is simply the diagonal matrix with these S's on the diagonal. Therefore, the determinant of the Jacobian is simply the product of the S's. So that is a rescaling layer. It's very simple. This one is non-volume preserving. So therefore, the entire nice model can also be non-volume preserving. Okay, so now we have defined these two rescaling and additive layers, and the nice model is simply the composition of these different types of layers. And we can visualize what this model can do. Again, this is an early model from actually 2014, 15. I forget the exact year, but this is an early model. These are samples from the paper. It was tested on what are some very simple data sets, but at least this is the first model. This is the first normalizing flow model that can actually generate some images. The planar flow model that I talked about in the previous lecture, that was never used to directly generate images. It was used as a component within a variational autoencoder to make the prior parameterizable and learnable.
But now this is a flow type of model that can generate images or, yeah, images of faces and digits directly by itself without relying on any other model family. Question. So the m theta itself does not have to be invertible. It's the entire so the m is just a mapping from one subset of z to another subset of x. But the overall mapping, the full z mapping to the full x, that thing in its entirety is invertible. Yeah. Okay, these are some samples from NICE on other data sets. Here we have a model trained on something called SVHN, which is a digit of house numbers, street view house numbers, and then CFAR10. Okay, so this doesn't look at all like CFAR10 samples. Right now, they can be indistinguishable with modern models, but at the time, this was a great result for normalizing flow models. Okay, and then the other extension, then a couple of years later, there was an extension to this model called real NVP by a similar subset of the authors, which can be thought of as a non-volume preserving extension of NICE. And here, what they did is that they modified the coupling layer to be, well, non-volume preserving. It still really looks like a coupling layer. We have the same identity mapping as in NICE, except that now the other part, the non-identity part of the forward mapping, has this additional x term. So this mu here, that's just our m from the NICE model, but now we're also rescaling this model z by something that can be a function of the previous, that can be a function of this subset. So now instead of only having an additive modification, which is the mu, now we also have a rescaling, which itself is learned from the other components. So alpha and mu are both parameterized by neural nets. So in some sense, it's combining the rescaling and the additive coupling layer of NICE, except that the scaling is also parameterizable on the z, and it can be parameterized by an expressive neural net. So that is the definition of the forward mapping in NICE. Again, the difference is this extra term here. Is it still invertible? Yes, it is still invertible. This is the inverse mapping. Again, for the first component, we perform the identity transformation. And for the inverse, we do the same thing because we know xd, we know z exactly. Therefore, using z, we can compute the alpha and the mu that was used in the forward mapping. That's just exactly these two terms. And because we know alpha and mu, and we know basically in here, we know this term, and this term when we perform the inverse mapping. Therefore, we can just rearrange terms and get an expression for this term. And you can observe that this is the same thing as in the additive coupling layer, but now I'm also dividing by the normalizing, by the rescaling factor, and everything still works out. Because we have this separation into two subsets, we can perform this type of modification. We can perform this type of inversion. Oh, and so it's volume preserving because what is going to be the Jacobian of this? So the Jacobian is going to be the identity on this set of components, but because here we now, so x as a function of z is now getting this multiplication term, well, this component is going to be the diagonal of these values. So therefore, the determinant of the Jacobian will no longer be 1, it will be this function, and because it's not 1, it's not volume preserving. Okay, so this is how a NICE layer looks like. And it came out a couple of years later, so they also used the bigger neural net and a lot of other practical tricks. So it's not just this particular
modeling choice. There were a few more choices that went in there, but you can see that it's able to generate much more realistic samples of human faces, of various types of bedrooms, certain natural scenes. You can see that these type of flow models can now generate more realistic images. And of course, there's been more work. So there was a follow-up on the real MVP model called GLOW several years after, and then GLOW can generate very, very high dimensional images with really good quality. It's also very expensive to run. It's very demanding in terms of compute, which is often the case for these flow models. But it's still based on the same architectural ideas as real MVP. Okay, and then another interesting thing that they showed in the real MVP paper is that you can still use it as a latent variable model. So what we have here in these figures are interpolations between 4 different vectors. So we start with a human face here, here, and here at the 4 corners. Or here, these are pictures of a building that are in the corners, right? So here, 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 and here, and we can interpolate between them along different axes using this formula, and it allows us to smoothly interpolate between human faces. I guess there were some questions in the previous lecture as to whether these latent spaces are useful because they're high dimensional. Again, recall that the shape of Z and the shape of X has to be the same. And this shows that the latent space Z still learns some interesting structure. So faces which are similar would get mapped to similar parts of the latent space. Again, empirically, this would require more study, and the fact that Z is of the same size as X, in some sense, does slightly disincentivize it to learn really good representations. But there is some level of interesting representations that is learned. Yeah. So I guess there's a question about would we find any interesting clusters in latent space? And I think it would really depend on the model, on the data set. It's not guaranteed to do this, but at least there is some interesting structure there. Clearly, images that are more similar to each other, like, I don't know, these two, are closer together in latent space. All right, so these are some samples. Okay, so we've seen a few examples of triangular flows. Next, I want to start making some interesting connections between autoregressive flows and the flows that we have just seen. So what are the connections between autoregressive flows and, autoregressive models and normalizing flows? Consider the following example. Let's say that we have a Gaussian autoregressive model. What I mean by that? I mean that we have, so X here is going to be continuous, and the model over X is going to be formed by applying the chain rule, and then each of these terms in the chain rule is going to be, so each of these terms is going to be a Gaussian with a mean mu and a variant, a log variance of alpha I. So each of these conditional terms is a Gaussian. In a lot of our previous examples, for example, in pixel CNN, or in the first example on autoregressive flows, we were using binarized MNIST as our running example. Therefore, in those examples, this conditional P of xi given the previous components, that was a Bernoulli, but it can be any distribution. So it doesn't have to be Bernoulli or softmax. It can also be a Gaussian. And the parameters of this Gaussian, mu I and sigma, mu I and alpha I, they're parameterized by neural networks of the previous components. And for the first component, because there's nothing to condition on, they're just 2 initial learned constants. So this is the model that we're going to start with. Consider this model. And now consider what sampling means in this model. Let's say we have somehow learned this model from data. Now we want to sample X from this model. The way that we would perform sampling is we could first start by generating a vector of normal variables, Zi,
And then from zi, we can get xi by the following transformation. So x1 is just going to be, so x1 is a Gaussian with mean mu log variance alpha. Therefore, I can form xi by just taking my taking my unit Gaussian variable z1, adding mu1 to it, and then rescaling by alpha. And now this gives me a variable x1 that's sampled from this distribution. So now that I have x1, I can use x1 to compute the mean and variance of the Gaussian over x2. And now that I have this mean and variance, how do I get x2? Well, in the same way, I have the mean and variance. I take my unit Gaussian sample z2, and then I add and rescale the mean and the variance, which gives me a sample x2 from this distribution. Okay? And then I can keep going. Once I have x2, I can compute the parameters of the distribution over x3, and then I can get a distribution over I can have the distribution. I can sample x3 from z3, and I can keep going like this to get the full sample. So this can also be interpreted as a normalizing flow because it defines an invertible transformation from the first set of random variables z to the second set of random variables x. I'm not going to prove that it's invertible, but you should see that it roughly is for the same reason as the nice and real MVP variables were invertible, where we essentially have here at each time step we have a subset. So you can consider x0 and x1 as being our two subsets, and then x0, x1 is one subset, x2 is the other subset. The same strategy applies here. I will actually have a detailed walkthrough of a related model later, but the idea is that in this model, sampling is a deterministic invertible transformation from a z that's sampled from a uniform Gaussian, from a unit Gaussian into a more complicated variable x. So an autoregressive model can usually be also seen as a normalizing flow model, and we can construct normalizing flow layers from pretty much arbitrary autoregressive models over continuous variables. Okay, and this is why we sometimes refer to these models as autoregressive flows. So there's even a name for this model. It is called the masked autoregressive flow. Okay, so it is literally a normalizing flow model that implements the transformation as the forward mapping. It implements that sampling algorithm that I just showed in the previous slide. So again, we define x from z in a recursive manner. The first component x1 is defined via the following formula. Now that we have generated x1, we go and we compute the parameters mu2 alpha 2 over x2. Then we compute the second component x2. And then we compute the parameters of the third component. Then we compute the third component, etc. So this defines a generative process. And you can also visualize what happens using this figure. So here we are computing the ith component of xi. And so once we're at the ith component, we have generated the previous i-1 components, which are here. And given these i-1 components, we can compute a mu and an alpha, right? So we use these to compute the mu and the alpha, which is what's needed to get xi. And now we take the ith component of the input zi, and we plug it into, and then we just apply the forward mapping. So here we have a graphical illustration of what's happening. So this is called a masked autoregressive flow model. Because the forward mapping is invariable, it's a valid flow. One thing to note, though, is that the forward mapping has to be computed sequentially. So this is a little bit slow. In order to compute x from z, I have to run a for loop, and I can't compute the ith component until I have computed all the previous components in my for loop, right? So I can't compute all the xi's in parallel. I have to compute them sequentially in a for loop, and I'm blocked on computing xi until I have computed x minus 1 and all the previous components. So in that sense, the forward mapping is slow. It is as slow as a regular autoregressive model. So if we wanted to implement this on a computer, it would run much more slowly than most other mappings, because we have to run a neural network in a loop and sequentially, and this is not parallelizable. Question?
So it's applied to images, I'm assuming also, this framework.
It can theoretically, yeah. So it's not the best.
So,
for images, people typically use a softmax distribution instead of a Gaussian, but it could also be applied to images.
okay. Okay. So because the Gaussian, the first one is going to be a Gaussian, and if it's a sequence of pixels and we're autoregressively generating the following one by sampling the first, so they're going to be more and more complex. And so if x1 was like the top left pixel, it would mean that we would sample the first one from a Gaussian distribution. I'm trying to visualize what it would look like.
First pixel will be sampled from a Gaussian distribution. They're all sampled from a Gaussian distribution, but the marginal over the first pixel is Gaussian, but the marginal over all the other pixels or audio samples would not be Gaussian. Okay, I just want to talk about this thing again. So this is the forward mapping. We can define an inverse mapping. How do we define the inverse mapping? Well, now in the inverse mapping, we have all of these x's, and our goal is to compute the z chart at the bottom. So given that I have all these x's, I can compute all the alphas and all the mu's in parallel. I have all the x's. I can compute all these parameters in parallel at the same time. And given that I have these parameters, I can now, again, in parallel, compute all the zi's, right? So the first z is just going to be a simple rescaling of the x, right? That it's just an affine coupling, so we can affine plus rescaling. So this is what we do here. The inverse is just straightforward. Yeah, scale and shift. Same thing for z2, because we know mu2 and alpha2, which were used to generate z2. We know them because we computed them here in the first step. We just again apply a scale and shift, and all of these steps can be done in parallel, right? And then, of course, because this is an autoregressive model, for all the same reasons as for the nice model, the Jacobian is going to be diagonal. It's going to be triangular, and then the determinant can be computed efficiently. Okay. And what's interesting here is that the inverse can be computed efficiently. So the forward mapping is going to be very slow, but the inverse is going to be easy. And this is actually interesting because it enables to do fast likelihood evaluation. Remember that when we in the change of variables formula, we have p of x equals p of z given x times this log determinant part. So if we are to train with a change of variables formula, this z of x has to be computed quickly. And that's what we can do here. Because the inverse mapping is efficient, at training time, we can compute the objective, we can compute our objective efficiently, and therefore we can compute the derivative of the objective efficiently, and training here is fast. But if we were to then take a trained model and try to generate samples from it, well, then we would have to generate z and then generate x, and that requires implementing the forward mapping, which will be slow. So the masked autoregressive flow model inherits the pros and cons of a regular autoregressive model. Training is reasonably fast because we can compute the inverse mapping efficiently, but the forward mapping is slow for all the same reasons as in a regular autoregressive generative model. Okay, so that's an MAF. It has these two properties. Can we do anything about these two properties? Can we get a more favorable? Can we have faster sampling? Well, there's another approach that we could use, which is called an inverse autoregressive flow. And I think the key thing to note to understand an autoregressive flow is that this mapping F, previously in an MAF, it was autoregressive in X, now is going to be autoregressive in Z. Okay? So what do I mean by this? Let's define the forward mapping. So in the forward mapping, I start with a vector Z, then I sample Z from some sort of simple distribution, like a bunch of Gaussians. And now I will compute the parameters mu and alpha, not from X, but I'll compute them from Z instead. And because I have already generated Z because I have generated Z in my first step, all of these are already available. And so the Z's are all available. Therefore, all the mu's and alphas can be computed in parallel. And then we can form the X's in the same way, right? So X1 equals X2, et cetera. So this is the same type of transformation, except that the mu and the alpha are now no longer coming, they're no longer functions of X, they're functions of Z. Or in other words, here I want to generate this Xi. I have already generated all the Zi, therefore I can generate these alphas and mu's in parallel, and now this mapping is the same given Z and alpha, but the alpha are a function and the mu are a function of this. So therefore, the inverse mapping is efficient. I already have all the alphas and mu's when I need to generate X. Okay, so this is a different mapping. It's a related but different type of forward mapping. So I claim that this forward mapping is invertible. Why is that invertible? Well, how would we do this? Let's say that we have X and we want to compute Z. Well, I can compute the first component Z1 from X1 by simply doing this shift and scale formula. Because mu and alpha are just constants, they don't depend on anything. I have them, they're parameters of my model. I can compute Z1 if I have X1. Now that I have Z1, I can compute mu2 and alpha2. Now that I have mu2 and alpha2, I can compute Z2. And then I can, because I do the shift and scale. And then once I have Z2, I can compute mu3 and alpha3 and so on. Right, so I can perform, so this is the inverse mapping. It exists, it's clearly invertible. This layer is invertible. But it has this interesting feature that now in an inverse autoregressive flow, the Z to X mapping is fast, but the X to Z mapping is slow. So what does it mean? It means that it's going to be slow to evaluate likelihoods, and therefore it will be slow to train for the same reason as I just explained earlier. When we train, we need to compute Z from X, and now this is slow. So this is a model that will be very, very, very slow to train. In fact, it's going to be impractical to train this from images directly, but it will still be useful. It's slow to evaluate likelihoods. It's fast to sample. And it's also fast to evaluate likelihoods of points that we have sampled. That's an interesting subtle point that I want to make, right? So if we have, so it's fast to sample, and let's say that for a point that we have sampled, we have also saved our Z's. Therefore, we can take our sample and we can evaluate its likelihood because the Z's are available to us. We don't have to compute them sequentially. We have the X and the Z. We have both the Z and the X for a point that we have sampled. Therefore, we can plug them into the formula, and it's fast to evaluate likelihood of generated points. I'll come back to this observation in a moment. Okay, but now this is an IIF. It's a different type of a regressive flow model,
and they're closely related. So I'm saying that they're transpose because if you take the x's and the z's, if you were to basically flip the two rows, you would get the other model. So they're not the same. They're in a sense in transpose of each other, and they have complementary pros and cons. Yeah. And then another quick point I want to make is that the real NVP and NICE are, in some sense, instances of an IIF in which we're not fully autoregressive. So in one layer of an IIF, we compute jointly a bunch of x's from the inputs. So here it says u, but u is z. Sorry, I took this figure is taken from another resource, and it implements this forward mapping where we shift and rescale the one subset of variables using parameters alpha and mu, which are derived from a different subset of variables. So it is an instance of an IIF framework. However, this is fast because we're not fully autoregressive, because we're doing it over blocks. Right, so normally in an IIF, in one application of this process, we modify only a single pixel. Here, a real NVP model can be seen as an approximation of an IIF where we modify an entire block jointly, but it's still the same idea, right? Given the input variables, we compute these parameters from the previous block, and then we use them to scale and reshift the other block. So that's the relationship between the real NVP and the IIF. Yeah, so here both sampling and posterior inference is fast, but because we're modifying multiple variables at a time, each layer is in some sense simpler. Okay, so now we have seen these two models. MAF has fast likelihood but slow sampling, and IIF has fast sampling but slow likelihood. So MAF is better suited for training and for density estimation. IIF is better suited for sampling, in particular for real-time generation. Can we get the best of both worlds? And that's what I want to talk about in the last 5 minutes, and it will give us an efficient algorithm for generating audio. And this is actually an important advance in audio generation that I want to talk about. So how does it work? First of all, let's quickly remember WaveNet. WaveNet is an autoregressive model for audio. It predicts audio samples one step at a time. And because audio is often sampled at tens of thousands of samples per second, a common sampling rate for audio is 44,000 hertz. So there's 44,000 samples in one second. This will be very, very slow to generate from this model because we have to generate samples sequentially. So we have to rerun this big neural net 44,000 times per second sequentially in a for loop. This is slow. What can we do to make it fast? So we're going to use this one interesting idea called model distillation or probability density distillation. The idea of probability density distillation is that I have some model, some probability distribution that I have trained, and I'm going to call this the teacher. So the teacher is a distribution over X. Let's say I have trained this. I want to train another model called the student to mimic the teacher. And I can train these models by minimizing the Kale divergence between S and T. We saw the Kale divergence. It's a notion of similarity between distributions. And this is essentially the formula for the Kale divergence that we're gonna maximize. So notice that this formula requires a few things. So first, here we're taking samples from the student model, right? That's just the definition of the Kale divergence. It requires an expectation over X. If I am to approximate this using Monte Carlo, I need to draw samples from a student model. Then I also need to evaluate the density of the student model.
This is what's going on here. I have S of X. And finally, I also need to have the density of the teacher model, which is what's doing here. So we have to find, I guess this is applicable if we can find a student and a teacher model for which these tasks are solvable. And now you can probably see where I'm going. Where would this be applicable? I guess there's hints already on the slide. We're going to apply this to WaveNet. And the result is going to be an algorithm, which I'm going to call fast WaveNet or parallel WaveNet. It will apply this idea to a WaveNet model. So the first step of the WaveNet algorithm is to train the original autoregressive WaveNet model using maximum likelihood estimation. And we know that that's tractable. WaveNet is a form of, it behaves like a masked autoregressive flow in my previous example. It doesn't have to be an actual flow. By the way, you can still train it as WaveNet, as long as you can efficiently train it and efficiently evaluate samples, which we evaluate densities, which we know is easy in an autoregressive model. And then to make it fast, after we have learned the original WaveNet model, we're going to train an IIF model to mimic this fast WaveNet, to mimic the original WaveNet. And that's going to be tractable because, first of all, we can efficiently sample from an IIF. That was the first requirement on the student model. And we can also evaluate the density of its own samples, which was that little observation that I made on the previous slide. Because we can cache this, when we generate X from Z, we can cache Z, and therefore we can evaluate it. And of course, the teacher can also evaluate the density of the samples of S. So now all the three criteria hold, and we can apply this distillation idea. And then once we have distilled a WaveNet into an IIF, we can sample efficiently from the IIF. And in practice, this can improve the speed of the WaveNet model by up to 1000x. And this actually is a meaningful change, and it makes real-time or close to real-time generation, depending on your hardware, the generation from WaveNet. It makes fast generation from WaveNet possible. And it's also a cool way of combining flows, autoregressive models, MAF, IAF. Okay, so that's it. Okay, I'll take 30 seconds just to do a quick recap of normalizing flows. So we saw that normalizing flows allow us to learn late variable models for which we have exact maximum likelihood learning, and we can also have exact posterior inference. That's something that we usually don't get. Now the cons are that it only works for continuous variables. The dimensionality of Z and X has to be the same, which is not great to learn the best possible representation of X. And also it imposes computational challenges, and it places constraints on the model type that we can use. And so in practice, normalizing flows, although they're great in theory, they're not widely used everywhere because it is just computationally intensive to train them. Yeah, for the same image quality, you have to have a much bigger computer to train these, so they maybe aren't as popular as some other types of models, but they're still interesting in practice, and they have a lot of interesting use cases, such as the one that I just showed you with WaveNet. So there are these two strategies for constructing flows. Okay, I'm going to pause here, and then in the next lecture, we will talk about GANs, which are going to be a completely different approach to generative modeling, which will actually, it will not care about likelihood. It will look at a different objective. So yeah, we did all this work in VAEs and in flows just to be able to compute the marginal likelihood well. We're going to start next lecture with the question of whether we even need maximum likelihood and whether we can get a better model by just a better and maybe easier to work with model by getting rid of this idea that we absolutely have to optimize maximum likelihood.